Sound check. Sound check. Yes. Let's see if I have someone in the class today. I'm waiting for connections. One concurrent viewer. I mean, I'd like you to write me on the chat why there is no one today in the class. So I'm curious because I came and it was the desert. Or maybe you're around. No one. Well, at least we have 6 concurrent viewers, and well, we can start the lesson. The feedback sometimes, well, we will leave without. In case there is some question, you write it on the chat, and from time to time I will have a look at it. So let's start by presenting the solution of the last episode exercise, the one on KD3, where basically you were asked to add 2 methods. Oh, we have one in class. I'm happy. So at least I have a feedback. Let's talk about the exercise of last time, where you were asked to add 2 methods to this this KD3 program that I've written. So let's see how it looks like and how I would proceed. Thank you. KD3.h. So basically, last time we developed together the infrastructure on the KD3. In the implementation that I provided you in the exercise, I added one extra bit of information, which is the use of a lambda. If you're familiar with lambda functions, basically lambda functions are functions that can be embedded in the code. So in our previous implementation, we had the split algorithm that was taking 2 iterators and a predicate. The predicate was used to determine on which side of the plane, basically, a point was lying, right? The use of predicates is, or of, let's say, embedded functions as in the form of function objects is quite typical of C++ and of generic libraries. Therefore, they provided, the designers of CPP in the last revisions, they provided a quick way to write predicates only where they are needed. So if you are in the condition that you have a sort algorithm or something that requires to have a function object specifying what is the order between the two elements, then you could either write the function object in the traditional way, or use the so-called lambda function, which is basically writing only the bracket-bracket operator inside the function itself. Now let's look at, for symmetry at these 2 pieces of code. 7 KD3. Again, KD3 dot H. This is the new version, and was it? All right. So I'm now trying to extend. This was the situation, the split function, as we had called it before. We said we called the split function between begin, end, and passing a predicate on the point type, constructing the entire predicate. The predicate was a so-called point type predicate that I think I've defined it here. That was implementing substantially this function called on the point by using the member variables center and direction. Okay? That was our initial implementation, and that was understood. Clearly, here I have a lot of code. And now imagine that I want to write the plain side predicate only in one point in my huge tree. Then, this looks ugly. I'd like to hide it and to put it only where it's needed. So in this case, what I could do is to inform my compiler, and now I will go to the right thing, to inform my compiler that here I have a function object. This function object is called the lambda function. This is the synopsis of the lambda function. At the beginning you have two brackets, left and right, and then inside you write, this is the so-called shares, like what context of the outside part the lambda should be accessible by the lambda function. By writing this ampersand, you're saying that within the function itself, you will be able to access anything which is visible in the scope right above. This means that if you would access the member underscore mean, you will be accessing the member underscore mean that is accessible over here. If you access the member dot normal, then you will be accessing the member not normal that is visible over here, and this is clearly the point, the argument of my lambda function that is consistent with the bracket operator of the predicate, which is this one. Okay? Very good. And then you write the arguments of the function, and then you write an arrow and the return value. So this means this is a lambda function that takes a point P and that produces a Boolean, and then inherits all variables from the invoking context by reference. This ampersand is by reference. If I would have written equals, I would have copied the variables. I could have been able to modify them. And then this is the body of the function. So it returns point minus mean dot normal. That performs basically calculates the distance between the point and the plane. And then returns true or false depending on which side it falls. It's exactly symmetric to this. Here I would have had to write point type scalar 0, but yeah, that was working anyway. Okay, guys? Understood? So this was a little bit, but there was nothing else in the exercise. Then what I was asking you is to fill two functions. One which was called best match fast, and the other one which was called best match full. What this function were doing was that instead of returning a set, they were returning just the best, the closest point in the ball, if it was available, or a null pointer if there was nothing in the ball around the pair. Is that clear? Now, a naive implementation of best match fast would have been to calculate the set and then to scan through the set for the minimum. But this is not what we would like to do, because this basically hinders the efficiency. Just imagine that the functions that we have written before, full search and fast search, return a collection of things. That means that they have to allocate or to extend. Every time they find a new item, then you have to create this item somewhere and then add it to the collection. That is an expensive operation. While if I just have to return one, I can be substantially faster. Okay. So what I'm asking you is to write the equivalent of these two functions, only basically specialized for the case that you want to find the best match in the two cases, so the point which is closer to the query. Basically that was it. Now, how would you proceed? I'm asking the single student in the classroom, did you manage to do this exercise?
No, I didn't.
You didn't. You didn't try or you didn't manage?
I didn't try.
Okay, that's important. But like, how would we proceed? I mean, I would proceed in the following way. Very first thing that I say, okay, if I have I have a linear search. I implemented this brute force search. Now I'm sure that I'm going to need this brute force search, but in a different version that returns me just the best one, right? So what I would be doing is to go in the part of the code where I had written brute force search, and I would implement a new method, generic method, that returns me the best in the set. Okay? Let's do it. Brute force search. I have this method over here. I just like copy it and paste it, because the difference here will be that I will have to change the how to say, I will have to change the signature of the function. I will have to change the arguments, because I'm not anymore returning a vector, but I'm returning, I'm not anymore modifying a vector passed by reference, but I'm just returning the best point. Okay? But I believe, I feel that the logics will be pretty much similar. So just like being lazy as I am, classical things of Grisetti, is that I just copy it, no? And then I will rename it. What this function will return? Well, it will return, I have the iterator, I have from the iterator extract the value type, which is going to be the point, and then I have to return a pointer to that, right? So I'll have to return one of those. And this will be my returning algorithm, the type that I return. Then I will call, what was the name? Brute force search. Best. Do you agree with me? I will call it brute force best. Then I'd like to keep the syntax similar to the one of the KD3. Like I will give it a begin, an end, I will give it a query point, and I will give it a norm. Like so, I'm giving it all what I need to have. I have all my arguments already like in place in the list of arguments that I want to pass. Okay. Then, this is kind of straightforward. Yeah.
So we want to find the point
Within the synopsis of this function is that I give you a range. I give you a query point, and I'd like you to, and I give you a radius of search. Okay, and I'd like you to return me within the point in the range, which falls in the ball, and that the ball having diameter norm, and that is closer to the query. This is what this function has to do, right? All right, like we know that, let's call it, all right, these are the type name that I inherited before. I just like take scalar, and then I would also using point type equals, just extract the point type because I like it. Using point type equals type name, iterator type, value type. And in this way I extracted the point. And then I can make this a little bit thinner. Right. Just I'm extracting the type to have something readable in my eyes. Right? Then I need to carry on the search. I will require a temporary maximum, and I would require also the best norm, the best point selector. The temporary and the best point that I found so far, right? So the best point will be a point type star, which is a null pointer. Now, because at the beginning I have no best, right? The matches I ignore because I don't need it. Then I iterate it between the beginning and the end. I take the point, and then I would write p minus query, blah, 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 blah. Smaller than square norm, and, or smaller than, right? It's like, in order to scan for the maximum, I have to calculate, like, let me be more verbose. I just extract the norm, the distance. I take a point, I subtract it from the query, I have the delta, and I calculate the square norm. Because I don't, why do you calculate the square norm? Because the square root is expensive. And anyway, it doesn't give me anything. I could easily work with square values. But if one wants to waste computation, you can always use the square norm. And then what you would have to do, if best or current norm smaller than best norm equals current norm, and best point equals the address of the point. Fine? That's it. No? But that was it. Was the first part.
It's not a stupid question, but the scalar is there for us so we can basically give a float or an int or double.
Repeat.
The using scalar,
Yeah?
type name, point type, double dot scalar, is basically a double or an int or?
Yes, it's basically, okay.
Whatever you do.
Like we assume, point type is expected to be an eigentype.
Oh, it's an eigentype.
Is expected to be. It's not, but it's expected to be. So if it's an eigentype, we can assume that the eigentype inside defines a using where you put the type of the scalar that you use on construction. So if you define a matrix of scale, so your colleague is asked, this scalar, we can expect this scalar to be either an int, a float, a double. I have to tell for the people at home. The answer is typically yes, but could also be, for whatever reason, some different type, because you can use the same infrastructure for something else. Anyway, the contract that you have with the user is that your point type inside defines a using, which is a scalar, using the type of the field scalar. Like for the matrices, when we did matrix scalar, matrix float int, or matrix complex int, okay, or auto-diff value. Okay, that's the meaning of the scalar. Just like to say, in this way, I want to cast it. I don't need to rewrite the function if I use it for different things. And I hope that for this simple scanning of maximum, there is no trouble. I mean, I'm constantly looking you because now you get all my attention. Mandatorily. I understood that today you have only 2 lessons, one at 9 and one at 5, right?
I think also the issue was I saw some other guys, but same for me, I thought the lesson would start at
9:30.
I forgot and I was 15, so I was confused, so I went up to learn something and then
Okay. Yeah, but I mean, that was last time we started at 9:15, I said 9:30. All right. All right, so now we have written it. I mean, now let's proceed and let's do the remaining reminder part of the exercise. Brute, force. The other one was KD3, eigen KD3, C dot, no, eigen KD3, H. All right, now, what were the functions to be implemented? Now you help me. Best match full. Okay, now this function over here is expected to return, if any, the best match that it finds in the graph. Okay? Now, no, best match fast. Best match fast, it's symmetric to the other one, which means that it doesn't try to search in the other part of the tree if the distance between the splitting plane is smaller than an epsilon, because we have found that the KD tree can be complete. So once again, I mean, you know, I'm lazy. I just think, oh, you know what, this resembles pretty much fast search, the fast search which brings every answer. I just like copy it over, and then I see how I can modify. The logics of this will be simply, you get a point, you get a query, you figure out whether this node over here is a leaf, because if it's a leaf, you can respond to the query just by returning performing a brute force for the best match in the range. If it's not a leaf, then you call the very same function on the left, depending on the splitting plane. You call it on the left or on the right. And it's a splendid example of tail recursion, because the last operation of the function that the function does is to call itself. And the compilers can optimize tail recursion by turning it into a for loop, while loop, which is good because recursion is evil in general. All right, like let me, like, shall we write it trivially? Like the case, it's a leaf. This is the case, it's a leaf. If it's not, I do not have a left leaf, a left, sorry, what was it? No, I always miss it. We are doing the fast version. If I do not have a left leaf or a right leaf, I'm just like gonna return, which means that I am, this node is so this node is a leaf itself, because if I don't have leaves, this means that I am the leaf. Then we can return, what was it, brute force best, I have a memory for the function, which is null. How did we call it? Brute force best. Begin and query node. Are we fine with that? Right. We close our function this way. Otherwise, we have to figure out whether we are on the left or on the right, and we can, you know, be verbose, and then what was it? We have this function, this piece of program that calculates the distance. I mean, let me copy it all, because if you understood that it's rather straightforward. We are doing the best match fast. So we calculate the distance from the split plane in the very same way. So if the distance of the split plane is smaller than something, we could also use the predicate here. Not much different. Left best match fast, but we have to return it, because it's gonna return it. And then we write the very same on the other side. No? End of the function. Okay? And now, like, we really did it. Okay, that's nothing spectacular. And then the final one is best match full, which basically will be pretty much similar to this, only that if the distance between the point and the split plane is smaller than the norm, then we have to try a search on the left for the best, try a search on the right for the best, and then we will have to pick up the best between the result coming from the left side and the result coming from the right side. Shall I will say slower. Now, this is the approximate search, in a sense that it tries, and once it takes a side of the tree, it never goes back. But we know that there is a loss of completeness if my query point is too close to the splitting plane. However, I know when my query point is too close to the splitting plane, and in this condition, I could carry on a search also on the other side of the tree. Okay, on the other leaf, on the other child of a node, right? Now, the reasonable thing would be to calculate the distance from the split plane, to figure out whether it's larger than plus the norm, in which case we can safely go on the right. If it's smaller than minus the norm, in which case we could safely go to the left, or if it is between plus and minus, minus norm and plus norm, in which case what could we do? We could try to do a full search, which is like a best match full on the left, which we're guaranteed by our recursion that returns us the best, which is on the left subtree. We could try to do a best on the right, which returns us the best that we have on the right, and then we have to return the one which is closer to the query point between the two results that we have on the left and on the right. Okay? That's the logic. So once again, you know, my laziness is spectacular. All right, now, what can we do? Best match full. For sure, we calculate, we for sure have to deal with the case of the point being a leaf, and therefore we copy the same piece of code before, right? And if it's a leaf, there's nothing spectacular that we have to do. Then if the distance from the split plane is smaller than norm, then minus norm, right? Then we can easily go to the left, okay? If the distance, else if, distance from split plane is greater or greater than plus norm, then we go to the right. And then we have the third case, right? Now, given that I could put another else here, but it sucks because it keeps on indenting. And so like, just like either this condition is true or this condition is true, and if none of the true is true, then I have the third case. So this means that I will have to carry on the search on the left, on the right, and then get the best. Okay? So let me inherit some, so point by start equals we calculate the left. Okay? I mean, I'd also do something like that. If I do not, if I have a null pointer in the left point, this means that I didn't find anything on my left subtree, and therefore I can just like return the p right. Okay, I'm so late. Yeah, well, all right. It's I'm thinking how to optimize it, but I mean leave it like that. If not p right, if we don't have the left, we return the right. If we don't have the right, we return the left. And then now we are in the condition that we have for sure both points here, right? If we have both points, we have to calculate the distance between the query and the first, the distance between the query and the second, and return the one of the two, which is the best. Okay? The left, so will be p left, p star p left, so I'm getting the point, minus query, dot norm, because I don't want to, or I mean, actually, like it's multiplying a point by itself is more efficient than like that. Okay? We calculate the distance to the left. We calculate the distance from to the right, right? And then we can return the left point on the right point based on the comparison of the distance to the left and to the distance to the right. Agree? A P left. Okay? This would be a way, or okay, this solves the exercise. Now let's see if it compiles. Probably not. Huh? Ah, yes, I made a mistake. Of course. Copy and paste error, number one reason of failures. Your colleague says you called it P right, but you calculate the distance from P left, which is true. So that wouldn't have worked. Okay? Clear? Well, perfect. Go ahead, go ahead. I mean, be interactive. I mean.
So now, just beneath the common workspace, this is a variable assignment.
Yes. We declare a variable of type point type, which is going to be vector 3, vector 2, vector whatever. It's with a pointer, right? Yeah. And then we invoke the function myself, which conducts a full search on the left subtree. But that was a mistake, because I have to say left.
Okay, now makes sense.
And there was another mistake. Excellent. That means I have to conduct the search on the right subtree, right? Copy and paste. And let's see if I made the same error here. No, here was consistent. Yeah, of course. I mean, that best match full, and here as well, I have to say best match full, because I have always to call the same function. Otherwise, I would lose completeness. Okay? So these are all the mistakes that I've made in 10 lines of code, just because of copy and paste. Okay? So, now, recapping. It's a leaf. Then, it's not a leaf, we calculate the distance from the split plane. If the split plane is, if I'm far to the left of the split plane, then I just like call the function itself on that subtree. If I am far to the right of the split plane, I just call the full search on the right of the subtree. If I am in the mid condition, then I carry on the search on the left, I carry on the search on the right, and then I pick up the best of the two. That's basically the message of the piece of program. Okay? And then the test will be the test will be basically the same as before, only that when we are interested in finding the absolute best, we very often have a loss of optimality in case of the large search ball in the fast search. Because then you really know, you might have 2 points which are very close, and then it's very easy to mistake them. And then in this case, if you are really interested in the absolute optimum, which is nearly never the case, then you have to use the full search. And like the remarkable thing of the test is that, okay, we have two blocks of the test. We construct 100 random points, we construct our funky KD3, this is the ball radius, 10, and then we compare fast, full, and brute force, exactly as before, and then we write down how many hits we found with the fast search for each query, how many hits we have found with the full search, and how many hits we have found with the full search, with the brute force search. And then if the numbers of the full search is different from the number returned by the brute force search, we say there is a mistake, we close the program because there was a serious error, because it's not compliant with what we expected to do. Then we do another different thing, because the full search and also the approximate search is guaranteed to be complete if you conduct a search in a set that really has the points that you're querying for. So if I'm doing queries with points which are contained in the set, I will for sure find it, even in the case of the fast search. Because this point will follow, because when constructing the tree, we use the very same logic that we were using when putting the point, when doing the search. We do a splitting. And so I will for sure find the best match. So this is not a correct test that I could do to take the very same points and to carry on queries. A much better test is that I create another different set of random points that I will use to query the points that I have put in the KD tree with in a previous generation of points. Okay? In this case, I will not have the exact match. And then when I ask, can you give me the closest point, this closest point will very likely not be contained in the original set. And so there I could appreciate the difference between the fast and the full search. Okay? So what we're doing is basically generating random points, right? And then we conduct queries on each of these random points in the set constructed, in the KD tree constructed with the points generated in the previous generation. And then we do the usual, the usual full search to figure out the numbers, and then oh, this was the cool thing. And then what we want to ask to our system is, hey, please, can you tell me, by using the fast search, can you tell me what is the best point that you have found in your collection by using the fast search? And then can you also tell me what is the best point that you have found in your collection by using the full search? Now, we are guaranteed that the full and the fast, the full and the full search and the brute force search return the same set of points by the previous experiment. Actually, we didn't test it. We should have compared the set. But believe me, it's the case. Now, what I would like to figure out is like how complete is, or how often the fast search returns the correct result. And in order to do so, I calculate the hit with the fast search, I calculate the hit with the full search, and then I have 2 pointers. I'll do 2 memory addresses of data which are in the same set. So I could easily figure out whether the 2 points refer to the same object or to a different object. And so what I will be doing is to figure out, to compare the 2 pointers and to figure out, are you the same or are you different? Okay, guys? Understood?
Because after this, you're searching for 2 points exactly the same, no? It might not be like a bit small error in difference.
This is what do you mean in this case? Where?
Yes,
so
here, because then you compare them. So you
I compare the pointers.
Yeah, you're searching for the exact point.
Exactly.
In both ways.
I'm searching for the exact point in both ways. And so if I would put this test here in the previous part, where I have the point preloaded in the set, I will get a list of OK. Let's test it. Because the set was constructed with the same point I'm using for query. In this case, I'm not. So there is a difference, there is a loss in optimality, because I will miss some of them. So if I would do this here, what was it? Oh no, I did it before, right? I did it also before, right? I did it also before in the case where I run this snippet of point of code to figure out, to compare the points returned by the two searches was also done in case of searches conducted. This is KD points in searches conducted in the tree. What I expect to find is that when I'm looking for points which I loaded in the tree already, then I will always find okay. What I'm expecting to see when I'm carrying on a search for points which are not loaded in the tree, which are different, is that I expect to find okay, no. Agreed? Clear? Because in one case it's complete. So this block of code, we search for points in the input set. We need to find a match. And the 2 matches for the fast and to approximate, for the best match, should be the same. In the other case, we search for a point not in the input set, we might That's the story. Let's run it. Let's hope it compiles. Will. Yeah, of course. I have an error because I used the old synopsis for the function. Oh, of course I have an error because it's not the same, right? I was copy and paste error. Ancora. Che vuoi da me? Ah, this is ugly. Read only variable best norm. Where is best norm? Ah, idiota. It's not constant. Because the best norm is a variable that we are going to change during the loop. Okay. Now we have eigen KD3 test, eigen KD3 test. Okay. Let's see. Too many points, too many searches. Okay, but this is, okay, very good. At the beginning, we have the full search, right? The full search. So this is the result. I look for the first point. I find 1 20, 20, and then it's okay. So when I'm carrying on the search, in the same set that it's used for, by using the same queries that are contained in the set, every time I get this okay. This okay means that the best match with the search and with the full and approximate is always the same. Okay, guys? Then there is an end line somewhere that is disturbing me. Probably I know where. And look. that it's ruining the output. And then let me write something that separates the two things. On more clear. Yeah. All right. Better. Okay, now, at a certain, oh yes. Here we have a brilliant situation. What we find is that we lose a little bit completeness because when I have 4 here, means that this is the number of points returned by the search. Like the approximate always, this returns 4, the other one consistently, the brute, and the other one they always return 2. Okay. Now, of course, then this is what happens when I use searches using query points not in the set. Well, very often I have a rather sparse set of points. It's perfectly fine not to find anything in a region. If I enlarge the ball, I will find something. But then often you see this no, which is consistent with the fact that the random search didn't find, the fast search didn't find the point, but the point is there, and this is also confirmed by the brute force search. Okay? Of course, the situation changes. How would you expect that the situation changes if I make the radius smaller? I expect that if I make the radius of search smaller, the fast search would go towards the full search, because the situation where I have to recurse on the left and on the right becomes dramatically smaller. I have a smaller slice. So, in this case, the situation is better. If I make the radius larger, then the full search and the fast search start to be divergent, because I might lose. It's very likely the condition where I'm very close to the splitting.
Because we're increasing the search area?
Yeah, we are increasing the search area. Your colleague says, because we are increasing the search area, and I agree. Okay, let's see. And then you see that I have many more okay. And also, like, I was having 2 little points, right? 2 little points. And so now let's stress it a bit, because we like to see the number crunching. The very first thing that I will be doing is to inhibit the full search, the brute force search, because it's bloody slow. And I mean, actually, like, let me do also this. Much better, eh? I'm just removing all the set business. Huh? Where was it? And then I'm just removing all the part where I return a set of points, right? I'm just interested in the best, the full, and the first. Okay. And then another thing, hey, I know you complain, bastard. Oh, yeah. Of course, I don't have any more variables. In this scope, I don't find anything. Please give me something to write. Okay, oh, this I can comment because these are all variables that I declared in blocks that I've now commented, so it's normal that the system cries. Comment region. Okay, no, and then remove the end line. Yeah, remove the end line for our eyes. Okay, this works. And then let's increase the number of points, right? That's what we want to do. Don't write it, right? Don't write it. I just want to count how often the situation is right, because otherwise the program spends all the time in printing things, and it's not what I like. And then we do the very same here. And then, come on, I was too gentle. I mean, you have the solution of the exercise in the folder solution, so let me butcher it. When I don't need code, I don't even like to see it. I don't want to see it. Via. It helps your brain. I mean, at least mine. You see, then you have the whole scope of your function in your eyes, and you can understand what's happening. That's why I don't write comments, and my students complain. Their problem. I have one of my students in the class. PhD students, I'm referring. All right. It's good for the eyesight, isn't it? Good hits, and then, oh. Huh? Makes sense. All right. Oh. We conduct on a KD3 of 1 million points, 1 million searches. We figure out that in the case of the complete search, in the case of the full, in case we are carry on queries with points in the set, we find all best matches. If the points are slightly different, the good matches are really much less, right? But what would happen if I basically reduce even the ball radius? You increase reasonably the good hits. Not that much, but you increase them. Okay? But am I doing... no. right? I have to use the same number of query points. Okay, much better. It's like that was my fault. I was conducting only 1,000 searches. Yeah, that's why I was getting at maximum. But 888 over 1,000 is not that terrible, right? No. No. We lose some, but it's not. There was a little bit contrasting me, this research. Okay, guys? We have a quite powerful tool, right? We conducted 1 million searches, over 1 million points in basically no time. Now, the interesting bit, now, of course, yeah, you want to profile it, right? Don't you? Yes. Let's profile it. I'm just disabling this initial part. I'm only interested in having, I'm only interested in the approximate business. And let's profile it a bit. Now this I'm gonna need. Well, we will have a number of good hits that doesn't. Oh, come on. Okay, not to understand any. 1 million points time. But that's also quite substantial time conducted in generation. Do you agree with me that I could run the query a little bit more often? I'm just running the query thing 10 times. Okay? So I'm conducting 10 million searches over 1 million points. 100. Why do you complain? I told you that I didn't need you. Not bad, huh? 100 million searches, over 1 million points. Okay? Very good. That's why C++ is not a bad thing to do, right? Now, we slowly went, fast but slowly, we went to possess a tool. I repeat, I'm only teaching you some technique on how to program, and I'm exposing you the characteristics of the language. The logics has to come from experience. I can give you some golden rule or some, advices on the thing, but there's no way you learn. I'm talking if you want to have a serious job, if you don't want to be just a box assembler, box composer. You will basically have to do trial and error, and then just like my suggestion, as I said to my students, my PhD students, I have 3 categories. My PhD students is fail, 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 fail. Keep on failing. Don't give up. Try to do things. Make them nice. Break them down, and then do them again. That's the best way to learn. Yeah, it's kind of how to say. If you like painting, you paint for painting. You don't paint for having a picture. Right? If you like programming, you program for programming. Okay, the result is the byproduct, but you do it because you like what you're doing and you want to do it well. And then you constantly revise the things. And every year I'm changing the code base because it's not right. And then while doing so, you have new research ideas. Because actually, like with the implant that we are building, we will figure out that we can do. Sometimes you look at the writing code and writing the structure, highlights a hidden structure of the problem. Like by doing this KD3, for instance, you might have ideas on how to solve different problems. Because you learn the abstraction. We will see examples of this later. But sometimes unveiling the structure of a problem through programming allows you to better understand the programs. Anyway, This is a little bit of philosophy, not good at it. Let's go to the lezione of today. Svides. All right. Oh, let me see if I have comments in the chat. Leonardo, there is not yet the solution on KD3. The solution, Leonardo asks, okay, now I'm answering questions. Why P left and P right have the same syntax? I don't understand where. If Adriano, you can give me some context, but probably like it was the same issue raised by your colleague in class. Is there a solution for the folder of KD3 on GitLab? Not yet, but there will be basically at the end of the lesson. Okay? And write down, I mean, we have a latency of some days, so you write down and sooner or later your message will come. All right, slides of today. Now, let's use what we have learned and also what you did not yet learn, but you might learn if you choose a brilliant, fantastic course, which is called Probabilistic Robotics, done by really good professor. Joking, it's like advertising. No. If you don't like these things, don't do them, but if you like them, you understand the logics behind, there's a course that has been established for that. And I'm not talking about programming, I'm talking about the class of problems that we're going to solve. Now, there's a classical problem that we have, which is registering shapes. So you have a set of 3D points. You take a picture, or with a depth camera, or with a laser scanner of a room. Then you move a bit, you take another picture of the same room, and you have two pictures of the same room. But they are not the same, because they are acquired from different locations. So if you think about the points, the 3D points which will be sensed by your 3D laser, that will be describing what we call a point cloud, which is nothing else than a collection of 3D points, they will be different because they are acquired from different locations. If you take a picture of this computer from here, it's different from a picture of this computer. Then what you typically ask us is to register, to align basically the 2 point clouds to form a unique one. Because in each of the point clouds, you will capture a part of the environment that you were probably not capturing from the first. So if there is an overlap between the two, you might be interested in aligning them. Okay? Registering the point clouds, or registering things in general, corresponds to find the relative transformation between one and the other that results in a maximally consistent alignment. Just to give a picture, imagine that we have this bunch of 3D points, no? We call it PI. Anyway, we have a bunch of 3D points taken from another position, right? And then assuming assuming that you know which point in the one cloud is which point in the other cloud, what you're interested to do is to find the relative transformation that expresses the position of the points in one cloud in the reference frame of the other. Now we are interested in finding this relative transformation. Understood? Is that clear? Conceptually, the problem? I have a set of points. You can imagine that each point on the one cloud is connected to each point on the other cloud through a spring, right? The points form a rigid body, and you would like to relax, and there are these springs which are tensed. These are the springs, right? And you'd like to relax the springs so that at the end they have zero energy. When they have zero energy, they actually move altogether the points from one location to the other, right? And by moving the points, they moved also a potential reference system which was attached to the points. Okay? The relative position of one reference system with respect to the other reference system, the transformation, is the transformation that maximally aligns these points. Understood, guys? One. Clear? Very good. Now, this is, hopefully it works. Never. Never. Will it? I'm confident. It was an animated GIF, but it doesn't work. Okay. Let me try if I do this. Oh, why don't you work? Terrible. This was a fantastic animated GIF on ICP. I mean, okay, now, the thing is that I'll describe what the GIF is doing. You see a yellow and a white surface. You should see that capture the same portion of terrain, no? Imagine that they are captured by an airplane flying with a line camera that gets the things. Then it moves on one direction, then it comes back, it moves on the other direction, and then you have two snapshots which potentially of the same area, which potentially have same overlap. But the plane moved and it's not perfectly localized. So what you would like to do is to move these two terrains, these two surfaces, one on top of the other, so that the consistency is the maximum. Okay, and you would see, you should see that this surface was before was somehow let's say in this location, or in this location over here, and then with ICP gradually it moves by running a registration algorithm. Gradually it moves so that you see more and more of this scattering between white and yellow that denote that the two surfaces are just compenetrating each other in that region. They are very close. Okay? Now, it's a complicated problem in general, the registration problem. However, for two reasons. The first reason is that you might have millions of points, so it's a large scale thing. And the second reason is that you don't have you don't know which point in one cloud is which point in the other cloud. Okay? This is the second thing that makes it complex. What is easy in ICP is to determine, given the correspondences, determine a configuration of a transform that brings them closer together. This is a mathematical part, which is easy computationally wise. Can be done very, very quick. I mean, how is my business? You will discover it. For those of you that do probabilistic robotics, you will discover it there. I mean, right now I'm giving you the algebraic solution of the problem already implemented. You don't need to do anything in this task. You will have to give this point matches this point, this point matches this point, this point matches this point, then you spin the wheel and then it returns you the transform. Okay? That's all what is required in this exercise. The mathematics behind is rather simple geometry, honestly, and they can be acquired when required. But I needed to give you this hint to make you doing your first ICP. Now, so said, the big problem of ICP is to determine the correspondences. Because you have 2 points and the points are anonymous. It's not that the point says, hello, I am a point number 1, and then one, oh, hello, I am a point number 1. I mean, you might resolve this implicitly if you attach some appearance, for instance, in images. You detect key points in the image and then you extract the descriptor, and this might help you. In the case of point clouds, it's a little bit tougher to determine which one is which, and also it's expensive because there are many. So, what can be done? Another story. What you can leverage is then you do the engineer and you say, okay, now I know that this problem here is tough because I know that the problem of determining which point is which is difficult. But let's put myself, I'm not interested in aligning two random point sets. I'm interested to continuously aligning a point cloud from different vantage points. Imagine I have my robot with its laser scanner, I get the points, then I move a little bit. I have an idea on how I move, then I get a new laser scanner, right? So I have a good guess of where I am at the next time, or I'm close to the optimum. Of course, there will be some alignment error, and I'd like to remove this alignment error. Okay? Now, in this condition, what typically a classical thing is approaching the problem with ICP. Now, I've been saying ICP 20 times, and you don't know what it means. ICP is an algorithm for solving the registration problem that it takes its acronym of iterative corresponding point. And it works as follows. You have an initial guess of how the 2 point sets are aligned, right? And then you interleave 2 phases. You run through iterations. you interleave two phases. A phase one, where, as given the current transformation, you try to figure out which point in the one set belongs to which point in the other set. Okay? Given the current configuration, given the current transform. And then, once you have these these configurations, these assignments, then you carry on the optimization. So you determine a new transfer. This new transfer presumably will improve, will improve the will improve the situation that you have found before, right? Because you are putting in strings and then you pull that strings. And then you do it again, and you do it again, and you do it again. So you interleave a phase where you look for correspondences, you determine the correspondences, you run the optimization, you get the transform, you apply the transform, you look for correspondences, you get the transform, you apply the transform, until you reach, you're stuck in a minimum, so to say. So if you are close to the minimum, this somehow works. There are a lot of caveats. What I will provide in this example over here is like just the intuition of a concept. There are many, many things that need to be considered when implementing a real ICP, but I just wanted to offer in this lesson, in this portion of the course, a stub, and coding it together, a stub of program that implements, that solves this registration problem for 3D random points. This is my aim. Now, the ICP loop works as follows. We have the input is an initial position of the moving cloud, because I call it, people call it reference and current or whatever. I really, really like to call it the two clouds of the two objects, one fixed and one moving, because otherwise you never know which one is there, what's going on. If you call it moving, you know that it's the one that is going to be moving during the optimization. Okay? We have an initial transfer. Professor, yeah? Yes. Yeah, go ahead. Yeah, of course. That's why you're here. Okay, we have an initial transformation, we have a set of moving points, we have a set of fixed points. And the algorithm works as follows. Until convergence. Convergence means since when you don't move anymore, determine the pairs, a point in the moving set and a point in the fixed set, based on some similarity criterion that could also be the distance. Find the closest, right? Under the current transformation x, which means you have to take the fixed points, apply the transform, right? Otherwise, you don't move them. The moving points, apply the transform, and then you get points in the reference frame of the fixed, ideally, and then for each of those points, look somehow for the closer, according to some distance matrix. Okay? We could use our KD3 with the best search to calculate the closest point, right? Because this will be boiled down just to do a bunch of queries, and we will be able to resolve the assignment problems. Okay? And then once we have this assignment, you calculate a new x as the transform that applied to the moving points minimizes the distance between the corresponding pairs. Okay? Obviously, I'm giving you the code for calculating the transform. And now I'm illustrating you an open loop ICP, like that I expect you to complete. Okay? I'm tempted to write it from scratch. Oh, let's see. Source. All right. Now, for simplicity, I will drop the templates in this one lesson, and we just like use the template classes that we have defined before, but we don't think generic. We just want to think about the simplistic problem on 3D points. All right. Then approaching the problem. Well, it might make a lot of sense, given the structure of ICP, to invent a data structure that contains two corresponding points. Do you agree, guys? And let's call this data structure point pair. Put it here. I call it point pair. Oh, cooler point pair. And it will contain a point that I call fixed and a point that I call moving. Okay, guys? I mean, it's not necessary. I'm just crafting it the first round. I could also put pointers to points. Doesn't. But also I know that, as I said to you about eigen, this point pair will be storing eigen objects. So I might run into alignment problems. To avoid this, all I need to do, it's a rule. If you have eigenobjects in a class, then you have to write this in the class, basta, or in the structure. This informs the compiler, redefines the new operator, but informs the compiler that, hey man, I want that in case you allocate these objects on the heap or wherever, these objects have to be aligned 16 bytes. Okay? And then we have a constructor just because we like it. No? Fixed, moving, initialize a list. And we have also an empty constructor because otherwise we could construct the point pair only by passing 2 points. Agreed? Clear? Well, then also we would like to define a vector of these eigenobjects. And let's call it point pair vector, which is a study vector of point pair, but these are eigenobjects, so we have to specify the allocation policy. Okay? I don't know if new compilers for 64-bit still require it. It would be much nicer not have to do this, right? But if you don't do this and then you have weird errors, then do it. Okay? This is some mechanics in the language that should be removed, but there's no other way of doing it. Okay? Because sometimes you're also interested in, this is optimized for speed, but sometimes you're interested in especially microcontrollers, in optimizing the code for memory space. And then, how do you deal with these two things? Speed means align them, make it easy, and so on. Memory speed means, so memory density, because you have maybe only 4 kilobytes or 3 kilobytes of RAM, means use every possible space, pack everything together. All right. Do we agree with this synopsis, with these two things? It's quite straightforward. Okay. I mean, this is a reminiscence of, we could just like write vector 3f vector, but in case we want to define ICP over a list, we don't care, basically. We could just like, if we want to have our ICP mechanics, machinery, to work on a list, we could write simply list. And then it would work on a standard list. Okay, that's why I have this using. But let's keep it this way. Okay? Vectors is something that people like. Then we have a constructor. Let's say ICP, I'm designing, so we have our class ICP, right? And which will contain the mechanics, the mechanism for ICP. I could also do it as a simple function, right? But I'd like to do it as a class because in this way you have like a scope with complete things. You want to run ICP, then you declare an ICP object, passing it a fixed container of points, a moving container of points, and then given that presumably I'll be using a KD3, you can also tell him how many minimum points in the list you have. Clear? And then we have two fantastic functions. Oh, well, stop. Then let's go on. What else do we need in this ICP mechanism? I'd like to have a function that optimizes, that I need variables. I need a variable that represents the current transformation. Let me call it x. That's an isometry. Fine? Isometry is rotation matrix, translation vector. That's it. A transform. When I'm calling
We also need like to skew and to, I don't know, shear.
No, we don't have shear, skew. It's isometry. There's a class of transformation, but isometry is a transformation that keeps the distances between the elements and keeps the angles. There's another class of transformation which is called scaling, that doesn't keep that maintains the ratios, but not it's like an isometry but with a zoom. Then there is a perspective, it's a family of transformation that's large. But isometry is the easiest one, the one that you encounter in robotics 1, I think.
So it's like a homogeneous.
It's an homogeneous matrix. It's an homogeneous matrix. It's exactly an homogeneous matrix. Nothing else. With 1 in the bottom row, 0, 0. All right? All right. This is a variable that I might need. Then I also might need a KD3. Because I'd like to construct, but for its nature, in my algorithm as policy, I have chosen to select as corresponding point the point in the transform moving, which is in the fixed cloud, which is closer to the point in the moving transformed cloud. So at each step I will take my moving cloud, transform all the points according to x, which is my current estimate. And then for each of these transformed points, I will select as corresponding point the point in the fixed cloud which is closer to it. Clear? So I will very likely need to construct a KD3 on the transform, on the fixed cloud. Because the fixed cloud is the one where I'm conducting the researches, the searches. Okay? Very good. But that's the thing. You remember that the process of constructing a KD3 shuffles the elements around. And we don't want it. So, how could we do? Well, we could create a known copy of the container, and then we can construct on this our own copy on this our own copy we could construct the KD3. So it makes perfectly sense to have that in my member variables I will have
We don't want the shuffling around because of speed.
see. I want the shuffling around because of speed, but I want that my algorithm doesn't enforce the user, doesn't modify the structure of the user. Conceptually, ICP should, I give you a fixed, I give you a moving. It's not that you have to change them. You leave them as they are. If you need to change them internally, you make a copy and you do your business, but this is a choice, okay? But in contrast, the moving cloud is never going to be changed. And so we can leave it, pass it by reference. So we have container type ampersand moving, and do we agree? And in the construct, and then KD3. How did I call it? A second. I don't remember anymore. I would declare KD3. Okay. Yeah. And we have a KD3. Just I put it in the using. So my KD3 will be a container will be a 3 node. Remember that the KD3 is instantiated on the iterator of the set. Will be a KD3, a 3 node that is constructed over an iterator of the set constituting the ICP algorithm. Agreed? It was like when we defined in our examples KD3 test and so on, it was quite straightforward for us. In this case, our ICP algorithm operates on a standard, like just to make it easy. The KD3 is instantiated on the iterator of the set of points, right? So I know that 3 node is my template KD3, but the KD3 operates on this. Sucks to write it this way, right? It's much better that I write the KD3 is constructed on an iterator of this container. So container type. Okay? And I'm just saying what is my KD3. Oh, let me write 3 node. I like it more. Okay, I'm populating the variables that I need for carrying on this machine. Is there anything else I need? Well, during the iterations, I might want to store the correspondences, to store a set of correspondences to pass to the optimization algorithm. Okay? Like the correspondence is the pairs of fixed moving, fixed moving, fixed moving. So I might need to have a point pair vector. Okay, let's go on. Constructor, what do I need to do? Very first thing that I need to do is to copy this parameter into this variable. Second thing that I need to do is to copy this parameter into this reference, which is constant because I'm not changing the moving. Agreed? The third thing that I need to do is to instantiate the KD3. Because the KD3 requires to be constructed from a beginning and end. Okay? So, 3. No, I have to use my variable, underscore fixed begin, underscore fixed end, and min points in leaf. And I've populated the 3 variable inside me. So I construct ICP, everything happens. Then the isometry, we can leave it as it is. Just this is for cosmetics. I just declare, I just resize once the vector of correspondences to the maximum to the minimum size between not to the to the maximum size between the size of the fixed and the size of the moving. Because pre-allocating a vector and then working on a larger vector in memory, but then using only a little bit of it, saves me from many reallocations while I do the things. This just like basically serves to say to the system, hey, don't waste the time in clearing this memory because it's like a scratch pad. We can say, no, reserve. Like, let's write it verbose, Giorgio, that's much better. Int I mean, why do you do so? Because you might have also multiple points in the query that corresponds to one point in the set with this in the reference. Are we happy with that? No. No. Reserve. Okay. Reserve. That was the method. Reserve is used to allocate, to tell, reserve this space on the container. No matter if the container is smaller, just allocate once that big room. Okay? This is used for the vector in particular. So you do once this operation and you're guaranteed that you will not have reallocations of memory if you don't put more elements than max size into the thing. Okay, this is a snippet, like my take, so to say. You don't need to do it, but it's educated.
So
All right?
it's not very important, but why do you use the auto keyword? Why just not?
Because this is a size t. This is an unsigned long int. It could write an int.
Okay.
But technically, this is a size t. They made this the million of variant of integer, right? There's the unsigned integer, the signed integer, the signed long integer, the size t, and whatever. And sometimes the compiler complains, says, "Oh, no, it's not the right type of integer." It throws you a warning, and that disturbs my eyes. That's the reason. But technically, it's an int. Oh, I'm going a little bit longer, and I think we'll have to finish later. But I mean, I think that I think that this impression of this coding from scratch is quite useful to you, much more useful than completing the exercises. Am I correct? So, like, I'd rather continue this lesson last time, even if we go a little bit longer. I'd rather to do the things slow and that everyone follows. So I have now to close the lesson. I'm sorry, guys. I mean, of course, you have the code, so you can have a look, because that's what we will see last lesson when we'll complete it. Of course, the code that I'm writing now will be different from the code that you have in the sources, right? But we will leave that, right? It's slightly different. It's not spectacular thing, but it can't be exactly the same. Okay? Then I say hello and I leave the room to someone else. Bye bye guys at home. Arrivo, me ne vado, scappo, fuggo, mi smaterializzo.